Hello, chemistry students. Today I wanted to give you a couple of examples on how to write chemical equations and balance them when I give you a sentence. So let's take a look at example one, where I have solid barium fluoride combines with aqueous aluminum chloride to form aqueous barium chloride and solid aluminum fluoride. So in order to do this, you need to remember how to write formulas. Remember that when you have a compound that's made up of a metal, like in this case barium, and a nonmetal fluoride, then that means that you first have to balance out the charges in order to make sure that your compound has a neutral charge. So you guys had a couple of exercises in the packet in order to do that. If you don't remember how, then you need to go back to your packet and practice that. Otherwise, this is going to prove to be a difficult task for you. So anyhow, let's get going. But of course, if you need to pause this and go back and look at something else, then do that. So first we have solid barium fluoride. Well, barium has the abbreviation Ba, and since that is a metal on the left of the stairs, if you look at the top of the column on your chem helper, it has a charge of +2. And we're combining it with fluoride, which has the abbreviation of F, and the charge at the top of its column is -1. And so if we do the crisscross method, where our 2 comes down here by the bottom of the F, and the 1 comes over to the other side, our compound formula is simply BaF2. And since in our equation we're saying that this is a solid, then we just need to write a little subscript of an S in parentheses to show that it's a solid. Now, our barium fluoride is combining with something, so we're going to add it to aqueous aluminum chloride. So for now, just ignore this aqueous. We'll come back to it. But first, let's just worry about what the formula for aluminum chloride is. So again, we have aluminum, which is a metal that's on the left of the stairs, and it is combined with chloride in a compound. So if you look for aluminum, its abbreviation is Al, and the charge at the top of its column is +3, while chloride is a halogen. It's in group 7. It's on the right of the stairs, and its charge is -1. So again, if we perform the crisscross method, we're going to bring our 3 down here by aluminum and bring our 1 over to the other side of aluminum like so, and we get the formula AlCl3. And now, since we said that it was aqueous, we're going to put a little aqueous subscript next to our aluminum chloride. Now, when these two combine, they are going to form, so we're going to draw our arrow, aqueous barium chloride and solid aluminum fluoride. So we do the same thing. Barium is Ba+2, chloride is Cl-1, and to write out this formula, we have to bring the 2 down by our chlorine, and we're going to have a 1, which again, we don't write 1s in chemistry, so we're not going to write it at all, but we assume that we have 1 atom of barium chloride in this formula. Since it's aqueous, put our little AQ in parentheses there. And there's our plus sign. We're going to also form solid aluminum fluoride. So once again, aluminum is Al, and that has a +3 charge. Fluoride is F, it has a -1 charge. And when we perform our crisscross method, we get the formula of AlF3, and we said this was a solid, so we're going to draw a little S like so. So there, we just did our skeleton equation. Now what we need to do is actually balance the equation. So now we have to add coefficients in order to balance this equation out. So I'm going to start by writing out my grocery list. I'm going to draw a line below the arrow. And now I'm going to list my elements. So we have barium, fluorine, aluminum, and chlorine. We have 1 atom of barium, we have 2 atoms of fluorine, we have 1 of aluminum, and we have 3 of chlorine. So as you can see, it's really important that you write out your formulas correctly, because if you don't, then your atom inventory is going to be completely wrong. So let's see what we've got on the other side. So we have barium is 1, we have fluorine is 3, we have aluminum as 1, and we have chlorine as 2. All right, let's start balancing. So our bariums are balanced, so I'm not going to start there, but let's take a look at our fluorines, where we have 2 on the reactant side and we have 3 on the product side. So what I'm going to do, since 2 and 3, like, they're not divisible evenly within each other, I'm going to look for the least common multiple of 2 and 3. And the way that you do that is you just multiply 2 times 3, which gives us 6. And what I'm going to do with that is I'm going to add coefficients so that I get 6 fluorines on my reactant side and I get 6 fluorines on my product side. So if I look at my fluorines, I have a little subscript of 2 here. And so if I put a 3 in front of the compound that contains fluorine, my fluorines will become 6, which is exactly what I wanted. But you have to remember that the 3 is also going to attribute to the barium, which means that I now have 3 barium atoms here. Let's continue on the other side. I also want 6 fluorines on my product side, so I've already got 3, so I'm going to put a coefficient of 2 in front of the compound that contains my fluorine, and now I have 6 fluorines. And remember that my 2 is also going to distribute to aluminum, so I have 2 aluminums. Okay, so now as I look at my numbers, and I'm just going to look back up at the top here because I just like to work from the top down. I have 3 bariums on my reactant side because I just added that coefficient of 3, but on my product side, I only have 1. So in order to get 3 bariums on the product side, I need to add a coefficient of 3 in front of the compound that contains barium. So now 3 times 1 is 3 bariums, but remember that the 3 also distributes to the chlorines. So I have to multiply 3 times 2 to give me 6 chlorines. Great. So now my bariums are good, my fluorines are good, but now let's look at my aluminums. I've only got 1 aluminum on the reactant side while I have 2 on the product side. So I am going to add a coefficient to the front of the compound that has aluminum, and that 2 is going to distribute, giving me 2 aluminums on the reactant side. But remember that the 2 also distributes to my 3 chlorines, and 2 times 3 is 6. So now if you take a look at my numbers, I have 3 bariums on each side, I have 6 fluorines on each side, 2 aluminums on each side, and 6 chlorines on each side of my arrow, which means that my equation is happy and balanced. Good job, Ms. McDonald. Thanks a lot. All right, let's look at our next example here. This is an example of an equation where you have to remember that there are some elements that are diatomic, meaning that if they are not combined with another element, you need 2 atoms of those elements in order for them to be able to stand alone. And those elements are high Broncliffe. So let's see if I can show you what that means. It looks like I forgot my close parentheses there. Sorry about that, everybody. So, but before we can go there, let's just take a look at what my reaction is. I've got aqueous dihydrogen dioxide decomposes to form liquid water and oxygen gas. So I have dihydrogen dioxide. So I don't have any metals here, so I am just going with what my prefixes are telling me. Remember that di means that we have 2. and this is aqueous, which means that it's dissolved in water. And you might be interested to know that H2O2, that's peroxide. So that's the same stuff that you can get as a solution, like you can get a bottle of it from Walgreens, and you can use it in order to clean out your wounds to prevent infection. Anyway, I digress. This is going to decompose. So this is my only reactant. It's going to fall apart and it's going to form liquid water. Well, we all know what water's formula is. That's H2O, and I'm telling you that it's a liquid, so we have to put our little subscript of L next to our formula. And we are producing oxygen gas. So here's where high Broncliffe is going to come in. Notice that oxygen is a part of high Broncliffe. And what that means is that I can't just write an O. No, it's diatomic. Oxygen is diatomic. It can't exist as a singular atom. It needs to be paired up with a buddy. So the formula for oxygen, for pure oxygen, is O2. And that's a gas. And that goes for any of those elements. Like if this changed and it said not oxygen gas, but it said nitrogen gas, then the formula is N2. If it had chlorine gas, then the formula would be Cl2. So none of these elements can exist as a single atom on its own. They've got to be incorporated into a compound, or if it's pure, then the formulas are Cl2F2, meaning that they're diatomic. You need two of those atoms of the element to come together. All right, but this is it. I've got my formula, my skeleton equation here. So remember again that this is called the skeleton equation. And now what I need to do is balance it out. So I'm going to draw my line and write out my atom inventory. So over on my reactant side, I have 2 H's and I have 2 O's. And guess what? I have the same elements on the other side. So here I've got 2 H's and I have 3 O's. 2 in my oxygen molecule and 1 in my water molecule. Now, some of you guys might be saying, well, why don't you just like change water to HOH? And I don't want to do that here because I don't have hydroxide. I don't have OH on my reactant side. So to use that trick would not help in this situation. So my hydrogens are good and my oxygens are out of balance. So I have a little bit of work here to do. And I know that some of you might be tempted to start adding coefficients to our oxygen molecule because it kind of stands alone. But the thing is that no matter what number you put in front of the oxygen, because you have a single oxygen atom in water, you're always going to end up with an odd number. So like if I were to put a 2 here, that means that I would have 5 oxygens. And then the trouble is that there's no number that you can multiply by 2 to give you 5 or to give you any odd number for that much. So I don't want to work with my oxygen here. My oxygen molecule. Instead, I'm going to work with water instead. So I'm going to start with the lowest even number and just see what it does to my equation. So I'm going to draw a 2 coefficient in front of my water molecule and see what it does. I might have to go back and change it. I don't know. Let's see what happens. So if I put a 2 coefficient in front of water, that changes the amount of hydrogen atoms I have to 4, and it's going to change the amount of oxygen atoms in my water to 2. But remember, I still have these other 2 in my oxygen molecule. So really, this changes to a 4. 2 oxygens in my water molecule, and I still have 2 oxygens in my oxygen molecule. So that's why I'm able to change this to a 4. Well, if you look now, that's going to make that super easy because now I can see that if I just put a 2 coefficient in front of my peroxide, That changes my hydrogen atoms to 4, and it changes my oxygen atoms to 4. And now check it out. I've got 4 hydrogens on each side of my arrow, and I've got 4 oxygen molecules on each side of my arrow. So bada bing, I am balanced and happy. All right. I hope that this helps you out. And if you have any questions, be sure to see me either before class or, of course, feel free to ask me during class. Have a great day, folks.